All right, let us do a third video on this series of introductory data structures and algorithms topics intended for students who are taking the first or the second course on data structures and algorithms. So here in this video series, I'm gonna give you explanations on topics that I've noticed that many introductory data structure courses they kind of skip and don't give enough attention. So hopefully these videos and the topics are interesting for students, first and second year students learning about the data structures and algorithms. So this third video's topic looks pretty simple, but there is surprising complexities hiding in there, and then gives us a good excuse to discuss various topics in algorithms and algorithm analysis in general. So this array search, and once again, so here in this topics in data structure GitHub repository, so we're gonna be looking at the array search demo that is showcasing the things that we discuss. First, we're gonna start looking at the algorithm that seems so simple that it doesn't even feel like an algorithm. But this discussion of the asymptotic running times and the worst case running times. So when you are given an unsorted array and your task is to determine whether that unsorted array contains a given element, so we realize that we have to look at every element. It seems obvious and trivial, but so then this has the consequence that if it takes at least 1 unit of time just to look at the one element, and we don't have some kind of a massively parallel computer or some futuristic quantum magic machine, so then the worst case asymptotic running time of whatever order we look at the elements is going to be linear. And this concept of inherent complexity of a problem. So we talked about in the data structures and algorithm courses, your professor has taught you that it is the algorithms that have a complexity, like for example, that the merge sort is n log n, and then insertion sort is O(n) squared in the worst time. But then this concept of asymptotic complexity, so we can also attach to a problem, so that the problem has an inherent complexity. So the best possible algorithm for that problem, what is its asymptotic complexity? And for many problems, so it has already been proven that we have the asymptotically best algorithms for those problems. And here, in the case of the problem, given an unsorted array, determine if it contains a given element. So the inherent complexity of that problem is O(n), because no algorithm can do better than look at each element. And if each element has to be looked at separately, taking at least 1 unit of time, so no algorithm can be better in the worst case than O(n). So now in this kind of a situations, when we have an asymptotically best possible algorithm for a particular problem, and it can be proven that we just cannot do better because that's how inherently complex that the problem happens to be. So now the only speed ups that we can do without changing the underlying model of computation is now that we crack open the big O notation. So we bring back all the constant factors, all the lower order terms and all the other noise, and then all the stuff that happens inside the computer outside this beautiful Platonic ideal of a high-level programming language program being executed. And then we just take our tools and start shaving down the constant factors. So let's look at the linear search, so appropriately called linear search for a couple of reasons. So it operates on linear time, and then it iterates through the elements in linear order. So the name is like a doubly appropriate. So here would be a simple implementation of the linear search. So for simplicity, let's just look at arrays of integers. So for an array of integers and the given element x to search for, determine if the array contains a given element yes or no. Now we can actually make this algorithm not to just return a Boolean, because in many situations the yes/no answer, even despite being true, is totally useless. So we might as well, since we are looking through all the positions anyway, return the position where we find each element, and then we have to determine, like somehow agree, how do we indicate the answer the element was not found. So let's use the artificial answer -1, because -1 cannot be a legal array index. So then we cannot confuse it with the answer that means that there is an actual element found. So return -1 if the element does not occur in the array. So now, of course, the pretty normal style would be to use a for loop or a for each loop to iterate through the elements. But I'm going to be using a while loop here to make it like easier to see all the operations that the method is going to be doing. So where we maintain an index I, giving the position that we are currently looking at. And then, so as we notice that we need to make two comparisons for each round. The first thing that we need to compare, so is that the I is strictly less than A length, so strictly less because we use zero-based indexing, like you're saying, people. So then, and then the short circuiting, and so notice that if the first condition turns out to be false, that the I is outside the bounds, so then the second condition doesn't get evaluated because of the short circuiting, and then we don't get an array index out of bounds expression. The second condition is evaluated only if the first one turns out to be true. So as long as we are inside the array and the element in that position is not the one that we are looking for, increment the position number. So we get out of this loop either by running past the end or finding what we are looking for. So now, so here we return as a one-liner using this Java expression if else. So the condition question mark expression to use if condition is true, colon expression to use if condition is false, like if else, but as an expression that has a value and is one line. So if the index is still within the array bounds, return the index, because it means that we got out of the loop by finding what we're looking for, and then otherwise return -1 if the index run past the end. So this now looks so simple, like how can we possibly do any better? Like it does like what it needs to do, but surprisingly enough, there's multiple ways to micro-optimize this, and then these micro-optimization techniques in general, so once you know them, you can use them to shave down the running time of your algorithms once you first get them to work. So always get your things to work first. There is no point optimizing something that doesn't work. So once it works and turns out to be too slow, then you can start trying to optimize. But so looking at this micro optimizations. So micro optimizations as opposed to algorithmic optimizations. Algorithmic optimizations improve the asymptotic running time. Like for example, if you have an O(n)² algorithm and then you come up with a better algorithm to solve the same problem in, let's say, n log n or O(n), like then you perform the very valuable algorithmic optimization. But we can define as micro-optimizations the ones that don't bring down the asymptotic big O complexity, but then shave down the constant factors. Like if you can shave down like 5% of a running time of some established algorithms, so algorithms that have already been squeezed as tight as they can be. So nothing to sneeze at, and if it's some classic algorithm, so shaving down 5%, that would be like a publication in a computer science academic journal. So micro-optimizations, how they work, they just reorganize the code and the data, all the small decisions, how you order them and combine them and tighten them. So make the execution faster, but as again, so micro-optimizations, they only shave down the constant factor, so they don't bring down the asymptotic running time. Now, micro-optimizations as a general rule, like I used to joke in my lectures, that if there was a rule that to become a computer scientist or a coder, you have to solemnly swear that never shall I again do any micro optimizations, that most of the students would actually be better off if they literally took this kind of a vow and followed it. So micro optimizations, unless you're doing like a really low level work, so most of the times they are counterproductive. Now, for the first reason is that when you do micro optimizations, as you, for example, see when we look at the micro optimizations of the linear search, then these micro-optimized versions, they are more complicated, they're harder to understand, they are more rigid for change. So the general way to do something, there is like a lot of slack and softness in there, and then the code is general, so the same parts of the code are gonna be doing like multiple things, but the micro-optimization tightens up the code and then fine-tunes the code for a particular situation. So the code inevitably becomes more complex and more rigid, because eventually becomes like a Gordian knot, so cannot be untangled. Then the second reason why not to do micro-optimizations at the high-level language is that when we think of the execution of the high-level language program, we're thinking about some kind of a Platonic, beautiful ideal, that the way that the program is executed, that every operation takes a constant time and all the memory accesses are equally costly, which is not the case at all in reality. So, but once this high-level programming language ideal is translated to the actual nitty-gritty of the machine code, and then that machine code is actually executed in some actual physical hardware that has all kinds of memory and other issues. So then this actual execution, so it may not fully conform to this Platonic ideal that we have in our minds when we think about the high-level execution. And now, as a result, like something that in principle would be speeding up the execution of the high-level program. So after this translation to machine code and then execute it in an actual physical machine, words and all, that these micro-optimizations might even be pessimizations, that the actual code execution becomes slower, that this is like a well-known phenomenon. So if you do micro-optimizations, so make sure that you have that heavy fuzz testing framework to test the code. Of course, you need the fuzz testing framework just to do the optimization, that you first write the working version, you test it properly and write the fuzz test that calculates the checksum of all the answers of the instances that you give it. And then after every optimization, you run that same fuzz test suite to make sure that your optimizations didn't introduce any kind of errors in there. But then this fuzz test suite, it gives you the running time also, so then you can verify that the optimization actually does improve the running time. Now then the third thing is the fact that like a parsing and compilation, it's been like a solved problem for the past 40, 50 years, but like there's nothing to it. Like the theory of parsing is like well known. And all the questions that remain are like so esoteric that they have no relevance for parsing and compiling any actual programming languages at all. So what have those compiler and other guys been doing? They've been working on optimizations, and the modern compilers at all levels, they do all of these, all kinds of optimizations to the code. You turn on the optimization switches to the max, and so the compilation takes more time, but then the execution of the code is faster. So a lot of compilers can perform many of these named micro-optimization techniques automatically on their own in all kinds of situations. So you don't need to do these micro-optimizations at the high-level language level. If living in a different country, sorry, I think I lost my connection there for a moment, that I had a TA who was heavy functional programming, and that kind of guy. So I found somewhere a list of named micro-optimization techniques. I think it was Bentley's classic material or similar, if I remember correctly. I showed him the list, and then a couple of days after, so he told me that basically at that time already like modern compilers were like already doing that, and that was like over 2 decades ago, 25 years now. So what have those compiler guys been doing for the past 25 years? I don't think that they've just been sitting on their laurels unless the whole field is fake, but of course it is not. So let's look at some of these micro-optimizations here in this example. This next technique is pretty useful. So this is actually very similar to the design pattern of the null object. So we, instead of having some references to be null and then be constantly testing whether a reference is null before you follow it, so you just have like a special object, a null object, and whenever your reference would actually be null, you just make it point to the object. But because it's an object, it has all the data fields and methods that then define that they like to do nothing, but it's not an error to follow a reference set to a null object. So then this null object acts like as a sentinel that is stopping you from running over the edge. So this next optimization of this linear search, so the exact same signature, exact same behavior. So let's call this sentinel search. So the sentinel search, how it works is that in this linear search, you notice we had to do 2 comparisons on every round. The first one testing that we are inside the array still, and then if so, look at whether that the element in the current position is the one that we're looking for. So the sentinel search eliminates the array bounds test. So making sure that we cannot run past the end of the array without hitting the element that we're looking for. So now we have to handle as a special edge case in the linear search. So suppose the array is empty. So we got to remember that the 0 is a number like any other number, and the empty arrays, empty strings, empty lists are just as valid as any other list. So now if the A length is 0, so then this condition is immediately false, and this doesn't try to access a non-existent element. But now in the sentinel search, so we have to handle as a special case that no matter what X we are looking for, if the length of the array is 0, so then X cannot be there because there is nothing there. So there is no there, there's a -1. And then otherwise, so we're gonna be placing this X to the end of the array to make sure that when we are running through the array and looking for X, we're gonna find the X there in the end if we don't find it any earlier. So we cannot run past the end of the array. Seems kind of clever. So we gotta, so that we don't ruin the array. So we take this original last element for safekeeping. So Java doesn't have like a Pythonic negative indices. I wish it did, but it's too late to put them in without breaking existing code. So we'll take the original last element for safekeeping, and then place this element X to the last position. And then this loop to iterate through the array. Notice we don't need to do the bounds check. So as long as the current element is not equal to X, keep going. So we cannot run past the end of the array because at the end of the array there is guaranteed to be X waiting. So we cannot run past it. Kind of simple but clever. But this sentinel idea, this generalizes to a bunch of other situations. So it's good to have this in your Swiss Army knife. So now I got to remember not to ruin the array that was given. So the methods, when they're given valuable arrays, that unless the method explicitly says that it will mutate the array state, so it should not do so. So restore the original last, okay, misspelled something, last element in place. And then, so now you got to be careful, we can have an edge case bug in here. So how do we know that we actually found the element? So if we found the element before the last element, so if I is less than the length of the array -1, or so if the last element was equal to X, so in which case I is gonna equal a dot length. So I cannot be past the end of the array, so we don't need to test for that in here. So if either case, so then we truly found it, so return the position I, so it can be the last position if the last element was a genuine X instead of the sentinel that we put in there, and otherwise return -1. So this now, so it's gonna be shaving off one comparison per round, but then it's gonna do a couple of extra operations before and after. So how much this is gonna be saving, so depends. If our arrays are humongous, so then the cost of avoiding the bounce check in every step, so that's also gonna be humongous. But for like a couple of elements, this probably is not going to be saving so much. So the time saved by not doing the bounce check is wasted by this before and after operations anyway. So there's after some cutoff point that this is going to pay off, but not before. So that this Sentinel technique is good to know. It's a very useful general purpose technique. Okay, and then far more classic micro-optimization. So compilers often do this on their own. This one is like in the series that it looks kind of stupid even. But again, so if it works and improves things, so it's not stupid even if it looks stupid. So this old expression is now well. So this another way to minimize the number of bounce checks, that if we do a bounce check in every round, now what if we cut the number of rounds in half by looking at 2 elements in every round? So then we're gonna be doing only half as many bounce checks. So let's see, but now we gotta be careful when we're looking at 2 elements at the same time, that what if the array has an odd number of elements? So let's handle so starting from the first position, so 0, that if the array has an odd number of elements, so then we could either make the first one or the last one to be the odd man out, but easier to handle the first one, so then we don't need to be constantly looking whether we're at the end. Well, we do, but we're not going to be looking at where in the second last position. So if the length of the array is even, so then we look at the first element, so post-increment the index, so increment after the use. So this difference between the post-increment and pre-increment is good to know. Gotta be careful with those. Don't make statements that contain multiple of those in the same statement expression, because that's just gonna be a kind of worms that I don't even want to crack open. But so if the first element is the X that we're looking for, so return the position of the first element, and then otherwise, so now as long as we are inside, so with this, like why this looks so stupid, like I always teach, don't repeat yourself, but this is like you're explicitly like repeating yourself. So exact same statement done twice, because if the loop runs half as many rounds, then we're gonna be doing twice as much work inside the loop, and putting these inside like a for loop, well, that kind of defeats the optimization that we're doing in here. So we look at the 2 consecutive positions at the same time. So if that element in the position I equals X, so let's say post increment I, notice that these and these are different expressions, so there is no harm in incrementing and decrementing the same variable, because these are in 2 different expressions. So where we post increment right away, and then we just pre-decrement before returning. So look at the 2 elements in one round. So then when we run past the end of the array, return -1. Now for this, once again, so if you look at the testing of these topics in data structure, so let's look at the test. So array search test. So I have a test array search that creates a bunch of random arrays, and then loops through looking at the elements either existing and non-existing. And then if the mode is 0, so use linear search, and if mode is 1, use sentinel search, and otherwise use unrolled search. And then so the checksum that is calculated from the answers, because all of these use the exact same random number generator seed. So then all of these are supposed to produce the exact same checksum also when they are running from the for the same randomly generated data. So asserting that after running the data, it is updated, the final checksum into n equals to expected. So if there is a bug in these three methods that I wrote, so then all three have the same bug because it manifests with the exact same checksum deviation. Also, gotta be careful, always remember to test your array algorithms for an empty array and a singleton array. So that, in my experience, reveals like 80% of bugs right there. So that's just remember that the 0 is a number like any other number. Don't be like ancient Romans who didn't know that the 0 was a thing. Okay, so next we're gonna be looking at what if the array is sorted? And so now we have the binary search algorithm, and I'm sure that your professor has shown you binary search, but I've noticed that a lot of material like presents binary search like even wrong, like this algorithm, the way that it's implemented, it's very easy to have a bug in there, and even if you don't, so a lot of people they present like a needlessly crippled version of binary search. Like there is no need to cripple it. You can have like the full-blown thing, and then when you have it, there's like a certain advantages that you get as opposed to using the crippled version. But now, before we look at this implementation of binary search, so let's this ask the question, like why is it generally better that your things are sorted? Like for example, if you have a street and that there is houses numbered, why is it good that houses are in ascending, or why don't we just give the numbers randomly, like in the order that the houses were built, or something else? And if you go to library, like isn't it better that the books in the library shelves that they are like in a sorted order, that they're not every book is like in some random place in the library, like it seems intuitively obvious that like being sorted is good. But like the question is like why exactly is it good? Like how is sorted data different from unsorted data? And the reason is this, that when your data is sorted, that when you do a comparison of individual elements, then this comparison gains superpowers. Like when we look at the binary search, when we are comparing like whether an element is greater than or less than the element that we're searching for. Now in the linear search, like because nothing was assumed about the order in which the elements were in the array. So now one comparison, when you look at this element, does the AI equal X or does it not equal X? So it doesn't tell you anything about the other elements in the array. You got a million element array, you look at the first element, the comparison tells you something about the first element, but gives you no information whatsoever about the rest of the elements. So we got to look at each element separately, so nothing like generalizes. But suppose your array elements are known to be in sorted ascending order. So in computer science, when we say sorted, we always mean sorted ascending order. So smallest first and the biggest last. So suppose this is known. So now let's what happens if you look at the element in the middle and compare it to the one that you're looking for. You're looking for element X, let's say 17. Let's say the middle element in the array is 42. So you conclude that this middle element is not what you're looking for because it's too big. You're looking for 17 and 42 is too big. But this one comparison now, it not only is telling you that the middle element is too big, but because it's known that this array is sorted in ascending order. So this one comparison tells you in one snap that all the elements in this second half of the array, that they're all too big because this midpoint element was too big, and then what follows is only gonna be same and bigger. So this one comparison eliminates an entire array, half of the array, from consideration. So even if you had a universe-sized array, or it doesn't even need to be an array, like it could be like just the integers. You're looking for the first integer that has the given property when it's known that the after integer has the property, then all the integers after to infinity have that the same property. So now you can use a binary search approach. It's just such a nice thing that the integers are sorted. Like imagine if the integers were not sorted, like the integers were like the first one is 7 and then like a 42 is the next, and the minus quadrillion is the third one. Integers were like a randomly like this, like some cruel god decided that that's how the integers are going to exist in the Platonic space. So integers wouldn't be very useful for our purposes, but the fact that the integers are sorted, so that's why they are like so nice. That's the thing. But now looking at just an unsorted, looking at the sorted array, so looking at the midpoint element eliminates half of the possibilities from consideration. So this now gives us the binary search algorithm, but now we're going to be really careful to get this right. And now that I say this, now I probably have some bug there remaining myself, but that's why we have these fast testers at least. So the binary search algorithm, the initial attempts that when you have an array, you have a position that you're looking at, and then you jump halfway back or forth, depending on whether the current element is too small or too big. Now that makes the super complicated algorithm with the complicated mathematics. So much easier way is to realize that let's use two indices. Let's call them low and high. So initially they span the entire array. And then this algorithm, the way it works, do I have it? I don't have it in here, but well, I think I have it in the comments. But the idea is that the position that we're looking for is always gonna be between these two indices if the position exists at all. So then once these indices initially they span the entire array, so then it's trivially true that if the array has that position is between the indices. And then looking at always at the midpoint element between the two indices, depending on whether the midpoint element is too big or too small. So then one of these indices is going to jump halfway towards the other one. So this interval from the indices low and high is always going to be half the size in single comparison. Eventually, these indices meet somewhere, and then because of the property that we maintain, that the position that we are looking for is always between these two indices. So once these indices are in the same place and we maintain that invariant property that the position that we're searching for is always between the indices, so that means that this is the position, it cannot be anything else. But now we got to be super careful so how to make this algorithm work correctly. So this is a notoriously difficult algorithm. A lot of teaching material of data structures and algorithms that I've seen presents it, so if not wrong, so presents the needlessly crippled version. So we're now going to be looking at the version that is not needlessly crippled. Now, once again, so whenever you write any array algorithm whatsoever, so run it with the empty array and a singleton array, like just to avoid the embarrassing poo-poo. These test cases are easy to forget. So now one bug that you can have, so is this expressions that make these indices jump halfway. So once these indices are next to each other, it's very easy to have a bug that the index actually just jumps in place, doesn't move. So now your algorithm is stuck in an infinite while loop. So don't do it. We got to ensure that no matter which way the midpoint element, however it compares to the x that you're looking for, that exactly one of these indices is going to move and that it actually moves, that it doesn't stay in place. We got to be careful with the expressions. But then we also got to be avoid the Charybdis here once we dodge skill. That if so the index that moves, that you don't jump too far, that you don't jump over the element that you're looking for. So we got to always jump, but not too much. So how do we do this? Oh, and then without avoiding the bugs, so this invariant that we're maintaining, like what if there is multiple copies of that element? So now this invariant that we're maintaining, so not only maintains that the element is between the two indices, but we can make it to trivially maintain that it is the leftmost occurrence of the element that is between the indices. Now imagine that your entire array was all the same element and you're looking for that element. So now we still guarantee that we're going to be finding the leftmost occurrence. Now, what is the big deal? Like, what do you gain? Well, if you only care about whether the element exists in the array or not, okay, it's not a big deal. But the fact that you're guaranteed to have this. Now imagine the following situation that I often have in my Python examples and labs. You're given a Python list, a humongous word list containing something like 250,000 English language words. And your task is to find all the words that start with the given prefix. Like let's say we give a prefix WOR. So then we would find world and worth and worm and like all those words. So now if you have an array that contains all these words in lexicographic order, so you just binary search for the prefix. So even if the prefix isn't a word, that it's not there in the list, so that we find the leftmost position that the element would be at if it was there. So this is also a useful answer. So the binary search, when it doesn't find an element, that most people just have it return false. Why? So you could just return the position that the element would be. Like if it was there in the sorted order, so you get the position of the next higher element. So that is the position that you would need to insert the element, moving all the elements one step to the right to make room so to maintain the sorted order. But even if you're not inserting anything, so in that sorted word list example, so you just search for the prefix, and then so it takes you to the first word that starts with that prefix in the lexicographic dictionary order. You know that you can start from that position and keep going right as long as the words start with that prefix, or you reach the end of the list after some C6 or whatever is the last word in there. So now so let me show you. So Java. So I was pretty shocked about this because I wanted to use this Java arrays binary search as the gold standard. So I write the fuzz tester that creates a random array and looks for a element, and then with the binary search here, and then my binary search, and then verify that both return the same answer. But observe all these binary searches, like these guys are even proud of it. If the array contains multiple elements with a specified value, there is no guarantee which position will be found. Okay, so why are you not using the correct version of binary search? Like I know what bug you have. Like I know the optimization that you have in there, and it's not an optimization. Like I really respect the Java guys, but this is like one of these bloopers that I just like I don't understand. Why in the and you could even in the next version of Java guaranteed to return the leftmost position because it doesn't break any existing code. Like any code that made some other assumptions, so that code was wrong to begin with. So you're not breaking anything that wasn't broken already. And then these guys have a pretty weird convention. I've never seen this anywhere else that if this returns a non-negative index, so then the element was actually found, and returning a negative index offset by 1 so that we can tell apart 0 and minus 0. Then this says that the negation of that would be the position that the element belongs to, but it's not there. So this I find this needlessly convoluted thing. But let's look at the binary search algorithm. So how to do it, and actually now there is like one classic bug here remaining, but so let's root it out in the end. So reading this, if you don't know the classic bug that the Google boys found somewhere in the 15 years ago, must be by now. But so let's see if you can spot the bug before we we reach the end. So binary search. Now the array is assumed to be sorted. So this is not going to verify the precondition if this method is given an unsorted array, so garbage in, garbage out. So you just get some kind of an answer, but so then the preconditions don't hold, so the method is not responsible for fulfilling the post conditions. The caller violated their part of the contract first, and therefore we are not obligated legally or morally to fulfill our part of the contract. The responsibility of things failing is always on the shoulders of the party that violated the contract first. They don't have a recourse if there is damages because we return a nonsense answer. Okay, so we have these two indices, low and high. So the low index and the high index inclusive to the subarray under consideration, initially the entire array. And again, so we have to handle, now when we return the position that the element would be, so what if the element is larger than the largest element of the array? So then we're gonna return as an artificial answer the one position past the actual last position, because if we return the last position, it means that the x is less than equal to the element currently in the last position. So we're gonna return the non-existent position, last position plus one, so the length of the array. So if the array is empty, we can handle that also, or the last element is less than the element that we're looking for, so return the length as the answer. So notice if the array is empty, so then it has no positions, not even zero, and we return zero as the answer. That is because there's nothing there. The x is by definition not less than anything there, and therefore if it was inserted, it would go to the position zero. So now, as long as these two indices have not met somewhere, where that is the leftmost occurrence as the invariant that we maintain guarantees. So now calculate the average, and now gotta be careful. So now in Java, so this because low and high are integers, so their sum is an integer, and integer divided by integer, so the single slash is integer division. So chops off the half, that's gonna be there. But because of this definition, what if there is an even number of elements? Then there is two symmetric midpoints, and then this integer division truncating, then it returns the position of the earlier one. So notice this asymmetry here. So what do we know about the indices low, mid, and high? Well, we know that because we are in the body of the loop, we know that the low is strictly less than high, but that is mid. So notice the asymmetry of the bounds. So because this is a truncating down integer division, so it is possible that the low and mid are equal. And this will happen when the subarray under consideration consists of two elements. So the low and the high position are adjacent. So then this formula gives us the low position. But the mid position is always strictly less than high. So what is asymmetry is going to introduce an asymmetry to the code. So we got to realize that if we try to make symmetric code because more symmetry, then you're going to have a bug in there. So now, next thing we got to be careful. Let's look at the midpoint element, and it's too small. So now, how far can we jump the low index? Notice if we say low equals mid, so let's leave out the plus one. So now we're stuck in an infinite loop whenever low and mid are already equal. So nothing changes in the while loop, so the while loop is gonna be running forever. Now we have to jump to mid plus one, but now the Charybdis, are we avoiding Charybdis here? Are we jumping too far? Is there a danger that we miss the position of x? No, because the element at the midpoint is strictly less than x. So therefore, it is okay to jump past it. Now, can low jump past high? No, it can't, because because mid is known to be strictly less than high. So therefore, mid plus one can be at most equal to high. So this low when you assign mid plus 1, it cannot jump over the high index. So the low and the high index, they're always that they define a non-empty interval. So here now careful. So when the midpoint element is too small, so then everything to the left of it is going to be too small, and we can jump all over them in one swoop, and we jump over the midpoint element also because it's too small. There's no harm in jumping over it. But now this asymmetry in the bounds, so notice the midpoint element is known to be strictly less than the high index. So the midpoint position is known to be strictly less than the high position. So when we bring high down to mid, so then high is going to be moving, it's not stuck in place. The high is going to decrease. So it doesn't stay the same because the mid is known to be strictly less than high. So far, so good. Okay, so now the audience is asking, cannot we jump to mid minus 1? No, we can't. Because the negation of this condition, the midpoint element is too small. Its negation is not the midpoint element is too large. No, the negation of that condition is midpoint element is same or too large. So when the element that we're looking for is in the midpoint, so then if we jump past it, so now we jump too far, but we have to jump to the midpoint. So notice the asymmetry between the jumps. So low jumps one past the midpoint, whereas high jumps exactly to the midpoint. So this is because of this asymmetry of the bounds. Low is less than equal to mid, and mid is strictly less than high. So this maintains the invariant can be proven that the leftmost occurrence, so the leftmost position where the element could be inserted without breaking the property that the array remains sorted, so it's always between low and high. So therefore, when these two indices are the same, the only possibility that remains is that this is the leftmost position where the element X could be inserted without breaking the fact that the array is sorted. So we just return the leftmost position. So now you can easily write the wrapper around this method, calls this method, and then looks at the element in the return position, and then if that element is X, return true, otherwise return false. So you can easily convert a method that returns more information to a method that returns less information, but not the other way around. So suppose you have a method that just returns a truth value. Does the element exist there, yes or no? So if you get that answer, so it doesn't, you cannot easily convert it to the position. So it's always better to return more information than less. So there's no such thing as TMI. So information can always be converted to less information, but if you got less information, you cannot magic it into more information. So this is more flexible. So this fact that this returns the leftmost position guaranteed, so this makes this algorithm more useful in some situations where when there is a multiplicity of the same element, we're going to find the first position, then we can just step one step at a time to iterate through all of them, and then the returns in the sorted array of words then finds the first word that starts with the given prefix, and then we can just step in alphabetical order to iterate through all these words constant time per word. Just need the array of words, don't need any kind of try or some other fancy structure. Okay, so this is the binary search. So did my viewers spot the lurking bug remaining? This is pretty funny because over the past week, dealing with the student code, all of them had an integer overflow bug. So int data type in Java has the maximum value of about 2 billion and plus some change. So if the values become larger, so then they roll over to the negative side. So Java guarantees the consistency of integer arithmetic over all environments, including the overflow behavior. But observe, so this bug is like nobody noticed it because it doesn't manifest. You need like a billion element array or bigger even for this bug to manifest. So it was the boys at Google. who first discovered this, so they would have erased that humongous. So this low and high, and because Java doesn't have unsigned integers, so then we have the range is not as big as it could be. But so suppose that both of these are like let's say 1.5 billion. So they still, you have like a 2 billion element array. You got like that much memory in your system. So even though low and high both are int values, so when you add these together, they overflow. So this result is some kind of a negative index, and now you get an array index out of bounds exception crash. So another principle here, that when you have like these expressions and they have like this data that doesn't have a name in your code, like in your code, the result of this expression is given a name, variable mid, but the expressions can have intermediate results and they are stored in the memory just like everything else. The intermediate results don't exist by magic. So even if it doesn't have a name in your source code, doesn't mean that it doesn't exist. So somewhere there is a memory location of 4 bytes of data containing the result of this 2 integer addition. So then that one is gonna overflow and give a negative result. So now left as an exercise for a reader, or you can Google for the answer. So how do you replace this with an equivalent expression? Careful with the edge cases. That gives the same answer, but guarantees that the intermediate results don't overflow. So you can use bitwise arithmetic and bit shift in there, or there's other solutions. So this, let's leave this as an interesting exercise for the reader. So be careful that you cover all the edge case situations correctly. So this, after that change, we hopefully have the correct binary search, but knowing myself, I probably made some stupid errors somewhere, so you can point it out in the comments. Okay, so let's finish up this video by looking at the incorrect version. So we can find this in all kinds of textbooks and slides. I've seen this like so many times. So now let's make an optimization. So otherwise it's like the same as the previous one. A lot of people forget the cases of the empty array also, but that's a different story. When we calculate this midpoint position, so let's immediately look at if the midpoint element equals x. So imagine that you have a huge array and the element that you're looking for is like right there in the midpoint. So then what's going to happen here is that in the high index is going to jump to the midpoint, and then the low index is going to be jumping until it gets to the same place, and then we realize that the midpoint element was there. So now somebody says that don't be optimized, notice my finger quotes in there, by testing whether the midpoint element equals x, so return the midpoint position. Okay, now technically, so if all you care about is the existence of the element in the array, yes or no, okay, this it doesn't give you the wrong answer, so far so good. But so first of all, this now breaks the property that we return the leftmost position of x. And okay, so you tell me maybe you don't care about that property. But the next question, is this really an optimization? So to determine this, so you can't just look at the best case. You got to look at the average and the worst case. So you got to especially look at the average case now. So yes, for all the arrays that the element that the x that you're looking for is in the middle, yes, this makes the algorithm work in constant time as opposed to logarithmic. Agree. However, for all the other arrays where x is not in the middle, you do this test for no reason. So you perform one redundant extra comparison every round. So especially if the array is such that x is not there. So now you're doing a log n number of redundant comparisons. So now if you think about it, so on one cup of the scale, we put all the arrays that have x in the middle, And then on the other cup of the scale, we put all the arrays where X is not in the middle. I think that this end of the scale is going to end up a lot heavier. So now the saving that we get for this small portion of arrays, that has to be truly humongous to make a difference in the average case behavior. For a small number of arrays, we get a big saving, log n turns into On, and then for all the other arrays, the main bulk, you get the constant time specification. So somebody can do the math, but I'm betting that this is not an optimization on average, and then the code got a couple of lines more complicated. So, and then we broke the useful leftmost position guarantee. So a lot of people don't seem to see the need for it, but this makes a whole bunch of things much better and easier. Now, then they also say that if you do this test, so now you know if you go past this hurdle, you know that the midpoint element doesn't equal X. So therefore, if it's not too small, it's gonna be too big. So now we can high can come to mid -1 as opposed to mid. So yay, we're gonna maybe do one less round of this loop. Now we'll make my algorithm super fast. I'm super elegant algorithm guy. I just happen to break a valuable property, but who gives a crap? So this incorrect version, like this, you can find in at least half of the introductory material, and then many have they don't handle the empty array correctly, or they have some other bug. So today's lecture illustrated that just the trivial problem, so seemingly trivial problem, determine whether an array contains a given element. So one version for an unsorted array, another one for a sorted array. So this hides interesting complexities. And don't get me started of the problem. Instead of looking for just one element, let's find an entire subarray that matches the given subarray pattern. So in a whole bunch of interesting algorithms in there. So we got regular expression states machine search, and we got a Boyer-Moore algorithm, and we have a Rabin-Karp hashing algorithm, and we have a Knut Boris-Pratt linear time algorithm. And I'm itching to make a video of those maybe in the future, but those topics belong more to like a second course in algorithms and such. Okay, so hopefully all the first and second year students watching this, hopefully you had a good time and I get some ideas of here. So maybe hopefully you got a good algorithm professor who teaches stuff properly. And for the next video, so I'm still thinking of a topic. I got a couple in mind, but I'll make one once I get the inspiration.